Good day and welcome back for part one of our discussion on the mean value theorem. In this section, we will investigate two key properties related to the derivative of a function, Rolle's theorem and the mean value theorem. And I do want to note that even though there will be times throughout this discussion where these topics feel somewhat abstract and maybe even unrelated to maximizing and minimizing functions, but in our next section, when we investigate how calculus affects the shape of a graph, we will be using many nice consequences that come directly from this mean value theorem. So without any further ado, let me just jump into Rolle's theorem, which is our starting point. If we have a function f that satisfies three key properties, the first property is that f needs to be continuous on the closed interval from a to b. It also needs to be differentiable on the open interval from a to b. And lastly, we need f of a to equal f of b. And if these three things are satisfied, then we are guaranteed that there will be a number c somewhere between a and b such that f prime of c is equal to 0. And recall from our previous discussions that f prime of c equals 0 typically, not always, but typically will correspond to the location of a local maximum or a local minimum. And I do want to really emphasize when it comes to using Rolle's theorem, which we will in a few minutes, we always need to verify or state that the hypotheses are satisfied. And more often than not, it's really going to be more about the fact that we just have to make sure to state it, as the functions we work with are typically reasonable enough to be continuous and differentiable where we need them to be. Now, I don't want to go through an extensive explanation or argument as to why Rolle's theorem is true, but a really nice feature is that we could just draw a couple pictures and I think I'll convince you that it must be true. So this third property is that f of a must be equal to f of b. So I'm just going to throw a few points into these graphs. And if I imagine connecting the two dots that we see with a continuous and differentiable function, that is to say, I can sketch it without lifting up my writing utensil, and the graph will have no sharp points or cusps. Now, there's really kind of two very big possibilities. One possibility is that it's just a line segment connecting the 2 points. The other possibility is it's not a line segment connecting the 2 points. But in either case, note what happens. In the first, I can pick any value c I want between a and b, and if we go up to the curve at that point and we draw the tangent line, it's horizontal. So f prime of c equals 0, which is precisely the desired outcome we wanted. Similarly, in the second picture, we see that if the graph starts going up and it's going to have to come back down to connect to the other point in a continuous differentiable fashion, there's going to be a local maximum somewhere. And the location of that local maximum corresponds to where the tangent line is horizontal, and hence, once again, the derivative is 0. And lastly, I'd like to note that Rolle's theorem is what in mathematics we would classify as an existence theorem. It tells us that a number c exists, but it doesn't tell us how many of them, and it really doesn't tell us even how to find them besides maybe setting up an equation to work with. So it is definitely possible to have multiple c values. In fact, you could have as many as you want by just getting in that corresponding number of local maximums and local minimums. So in this picture, we can see approximately a c1 and a c2 value corresponding to these local maxes and local mins we see, and in either case, f prime of c1 is 0, and f prime of C2 is equal to 0. So let's now pause for a moment to look at an example of where we can use Rolle's theorem. So let's show that the cubic polynomial x cubed plus x minus 1 has exactly one root. And I'm going to note the key phrase here is that it has exactly one root. And in order for us to explain that this is true, we are really going to need to be able to show two different things. We are going to need to show that there is a root and no more than one root. So part 1 is going to be to show f has a root. And just the reminder, what we mean to say that it has a root is that there is some value, call it x1, when we substitute it into the function, we get out 0. And this is going to be a familiar type of the part of the problem. We can explain why this is true using the intermediate value theorem. And to show that there is exactly one root, we're going to have to go on to a next part and show that f does not have two roots. And in order to show that this function does not have two roots, this is where Rolle's theorem is going to come into play. And before continuing on, I do want to point out that I realize this seems like a rather abstract example, but it does illustrate some nice mathematical reasoning, and it ties together some mathematics we saw earlier this semester with the intermediate value theorem, and it nicely illustrates where something like Rolle's theorem might actually come up. And I'll also point out this isn't an argument I would expect you to immediately come up with on your own, but hopefully as we kind of talk and write our way through it, it's something that if you encountered again in the future, you would understand and be able to recreate as necessary. So part 1, we've already indicated kind of what we want to do. We want to use this intermediate value theorem. And there is a picture that I'm kind of keeping in the back of my mind. If I want to show a function has a root with the intermediate value theorem, one way we could do that is if we can find some input where the function is negative, some other input where that function is positive, and we connect them with a continuous curve. Somewhere in between, it's going to have to cross that x-axis, and it's going to have a root. And recall the key hypotheses that we need to use the intermediate value theorem is a continuous function. Okay, so let's go ahead and note that. Since f is a polynomial, what we know is it is continuous everywhere. And while we're at it, since we know we're going to use Rolle's theorem in a few minutes, let's note that it's differentiable as well and just get that out of the way. So since f is a polynomial, f is going to be continuous and it's going to be differentiable everywhere. So I'll say from minus infinity to infinity. In my earlier comment related to verifying or stating that the hypotheses of Rolle's theorem is satisfied really comes down to a statement of this form. Because it's a polynomial, we are guaranteed it is continuous and differentiable. And now, in order to relate this back to the picture that we've drawn, we need to see if we can come up with inputs to our function that have a negative output and a positive output. And looking simply at this minus 1, that indicates to me an input where I will have a negative output. So let's just go ahead and just observe, or I'll just say note, if you calculate f of 0, you get back minus 1. Can you think of an input that will give you out a positive output? And there's not a unique answer, there's many, but note if we substitute in 1 for x, we just get back 1, and that's a nice, obvious positive output. now we apply the intermediate value theorem. So since f of 0 is less than 0, which is less than f of 1, the intermediate value theorem, IVT, implies that there is a c in between 0 and 1 with f of c equal to 0, where the number c is corresponding to this root we've seen in our graphical intuition. And that does it. What this is showing us for part 1, just to kind of make it as clear as possible, f has at least one root. Now, we don't want to show that it has at least one root. We want to be a bit more precise and show that it has exactly one root. And the way to show that there's exactly one of something is to first show that there is one, check, which we've done, and then show that there cannot be more than one. And this is where we're going to use a new to us in this class argument that's a nice argument to understand. We're going to proceed by what we would call contradiction. So what we are going to do is pretend that x equals a and x equals b are roots of the function f. So what we are going to do is just assume or pretend for the moment that there actually are two roots. So we're going to assume the opposite of the desired conclusion. And the idea being is, if this leads us to a contradiction or a false statement, that means the assumption that we started with cannot possibly be true. So we are pretending this is true with the hopes that it will lead us to a false statement so that we can conclude it's not possible to have these two roots. So stick with me for a moment and let's see where we end up. So we're pretending x equals a and x equals b are roots of f. So that is, we're supposing f of a is equal to 0 and f of b is equal to 0. And note, this should be looking familiar. If you go up towards the top of your page, you'll note that we have a function which is continuous and differentiable everywhere. And specifically, f of a is equal to f of b. That is, the hypotheses of Rolle's theorem are satisfied. Okay, so now we're good to go. So by Rolle's theorem, there is a c value in between a and b with f prime of c equal to 0. And just to be as clear as possible, note we have already stated all of the hypotheses of Rolle's theorem above. Continuous differentiable f of a equals f of b. So there is nothing else that we need to state besides noting that we are using Rolle's theorem. This is an issue, though, because if we were to differentiate our polynomial, we would have 3x squared plus 1. And can the quadratic 3x squared plus 1 ever be equal to 0? And the answer is no. So this is never 0. But just a moment ago, we said it is equal to 0 somewhere. And if we're saying it's never 0, that means this thing we started by pretending that there are two roots cannot possibly be true. So therefore, there can only be one root. So there cannot be two roots. And just to make sure we're all on the same page in terms of this observation about the derivative, if we were to look at the graph of 3x squared plus 1, that's a polynomial that has a vertex a quadratic that has a vertex at the point 0, 1, and it opens upward. It never crosses the x-axis. So we have shown that the polynomial has a root and that it does not have two roots. So what we should do now is get a conclusion in here and just make a simple statement. F has exactly one root. And as I mentioned before starting this example, it is more on the abstract side, but I do think this illustrates to us some nice mathematical ideas related to the intermediate value theorem and Rolle's theorem. And it's not something I would expect you to just look at and instantly come up with on your own, but hopefully something that as we discuss, you can follow the details and follow the ideas involved. So that completes our discussion of Rolle's theorem, and we are now ready to move on to the mean value theorem. So stay tuned and take care.